Today we will solve GATE 2023 questions. This is a question from algebra. It is question number 46. So it's saying that consider the two rings S1, this is a ZX mod 2 comma x cube, and Z2x mod x square. Where this meaning this 2 comma x cube is meaning the ideal generated by 2 and x cube in ZX, and x square bracket is meaning that ideal generated by x square in Z2x. Okay, and four options are given. Every prime ideal of S1 is saying maximal ideal. Option B is S2 has exactly one maximal ideal. Option C is every element of S1 is either nilpotent or unit. And option D is saying there exists an element in S2 which is neither nilpotent nor unit. Okay. So in order to solving this one, this is the NPTEL reference. Okay. So let's start from the first option. It is saying for S1, every prime ideal of S1 is maximal ideal. So S1 is basically ZX mod ideal generated by 2x and x cube, right? So we have to show that the first option is correct, mean every prime ideal in S1 is a maximal ideal. So you will show that every prime ideal of S1 is maximal ideal. Okay, so let P be a prime ideal in S1. Let P be a prime ideal in S1. Then P will corresponds to an ideal in ZX which contains 2 and x cube. Then P corresponds to an ideal let's ideal of ZX containing two and x cube, right? This. So let's say let Q be that. Q be the prime ideal. So it will corresponds to a prime ideal again, right? So let Q be the prime ideal corresponds to P. To P. Okay. So Q is a then ideal. So basically, so 2 comma x cube. This is Q. This is ZX. So therefore, x cube belongs to Q, right? And Q is a prime ideal, which means that either x or x, because x cube you can write x into x square. So therefore either x or x square belongs to Q. So if x belongs to Q, then it is fine. So it is saying that therefore x belongs to Q, which implies you are saying that we are claiming that x belongs to Q, which implies x belongs to Q. Why this is true? As Q is prime ideal, right? As Q is prime ideal, so x cube you can write x into x square. So if x is belongs to Q, then we are done. If x square is belongs to Q, then we can write again x into x. Then x will again belongs to Q, right? So therefore if x cube belongs to Q, then x belongs to Q. And also 2 belongs to Q, right? So therefore the ideal generated by 2 and x, so this contained in Q, right? Now we will show that this ideal, the ideal generated by 2 and x, is a maximal ideal in Zx. Now claim that 2 comma x is a maximal ideal in Zx. Then what will happen? If it is maximal ideal, then it must be Q, right? Then it has to be Q because Q is containing 2 comma x. So let's prove this first. Why this is a maximal ideal in Qx. So suppose not. Suppose this is not true. So then what is the meaning of this? So means let P1 be the ideal which contain 2 comma x cube x and which is maximal, and P1 is maximal. Or means P1 is ideal which contains 2 comma x. Then we will show that P1 is Zx. Then it is the meaning that 2 comma x is a maximal ideal, right? So we will show P1 equals to Zx. So as P1 is strictly contain 2 comma x, so means let some small p which is belongs to P1, but P does not belongs to in this ideal 2 comma x, right? And as P is a polynomial in Zx, so therefore we can write P as, how you can write any polynomial? You can write a naught constant term plus x times some polynomial, right? Gx, or gs again belongs to in Zx. Now here note on an important fact that a naught cannot be a multiple of 2, means it must be it should be co-prime of 2, right? Note GCD of a naught should be a naught and 2 should be 1, mean a naught should be co-prime to 2. So what will happen? So if means a naught is a multiple of 2, then what will happen? Means not GCD of a naught and 2 is 1, then a naught will be multiple of 2. So then because then P will be strictly then because P is generated by P is, you have written a naught plus x, then P of x will be 2m plus xgs, so which implies this belongs to 2 comma x cube, and which is a contradiction, right? Which is a contradiction, which is not true. So therefore GCD of a naught and 2 is 1. So what is the meaning of this? GCD of a naught and 2 is 1, means there exists alpha and beta belongs to Z such that a naught alpha plus 2 beta is 1, right? So a naught, this is because P is in this prime ideal P1, so a naught is in P1 and 2 is also in P1, right? So therefore what will happen if this a naught and 2 are belongs to 1, which implies a naught alpha plus 2 beta belongs to p1, which implies one identity element is belongs to p1, and p1 is an ideal. If identity is belongs to element is belongs to that ideal, which implies that ideal should be the whole ring, right? Because you can multiply by any element, it will again belongs to that ideal, which implies p1 is the whole of zx, right? So therefore what this we need to show, right? p1 is whole of zx. So therefore we proved our claim that 2 comma x is indeed a maximal ideal in zx. Therefore 2 comma x is a maximal ideal in zx. So what we will then get, then as we have 2 comma x is a contained in Q and 2 comma x is a maximal ideal, so 2 comma x must be Q, because Q is we have the corresponding ideal we have taken which contain 2 comma x cube and in zx, and it is of course proper. So 2 comma x is basically Q, and Q is a, what is Q, where Q is a prime ideal in zx, right? And we have seen that 2 comma x is a maximal ideal, which implies Q is a maximal ideal in zx. So then by correspondence, because Q is a corresponding ideal of P for in this ring z comma z mod 2 by x cube, so therefore P is the maximal ideal. So P is the maximal ideal in this zx mod 2 comma x cube. So we have started with this P to be prime ideal. We have seen that this is a maximal ideal. So therefore every prime ideal is maximal ideal in S1. This is S1. So therefore every prime ideal is maximal in S1, which is zx mod 2 comma x cube. So this is the first option. So we have shown that this is correct. Every prime ideal in S1 is maximal. Now let's do the first C, option number C, because it is telling about S1. Then we will do the B and D for S2. So let's check for S2. C means it is saying that every element of S1 is either nilpotent or unit. Okay. So here for that we will use one result. So this is a standard result. Let me write. So this is for P. No, sorry, A. Now we are doing C. Let me write one result first. Let A be a commutative ring with unity. Then an element A is nilpotent if and only then A, which belongs to A, is nilpotent if and only if 1 minus A or plus minus A is a unit in A, right? So let me write the definition. What is this meaning that A is nilpotent? A in A is called nilpotent if A to the power n equals to 0 for some positive integer n belongs to Z plus. And unit, let me write also the definition for unit. A belongs to A is called an unit if AB equals to the identity element for some B in the ring A, right? So these are the definition for nilpotent and unit element in the ring. And what this result is saying that in a commutative ring with unity, that element is nilpotent if and only 1 plus minus A is unit. So we'll use this to conclude our result. Okay. So what you have to say in that? So that every element of S1 is either nilpotent or unit, right? Okay. So S1 is basically ZX mod 2 comma x cube. How general element will look like? So let P belongs to S1. So then P of x, you can write A naught plus x times Gx. So this is the coset, means I am writing it here, right? So this will look like any element in S1. Where what will be this A naught? Note that A naught will be 0 and 1 because 2 is here a 0 element, mod 2 basically, right? So A naught is either 0 or 1. So what will happen? So first take A naught equals to 1. Let A naught equals to 0. Then what will happen? So P of x will be x Gx 2x cube, right? Now if you take this px cube, then what will happen? Note that here x cube is a 0. So this will become the 0, right? So px cube is a nilpotent element. Means px cube is 0, which implies px is nilpotent. So not 0 means here the 0 elements is basically 2x cube, right? So px is nilpotent. Now let A naught is 1. Then what will happen? So then px will be 1 plus x Gx plus this. This is the 0 element. So this is a. So we have seen earlier that x Gx is a 0 element, as x Gx is nilpotent. In S1. So by the above result, one plus x Gx of this coset, which is basically px, is unit, right, in S1, right? So we have these two cases. We have seen that if A naught is 0, then px is nilpotent, and if A naught is 1, then we have px is unit. So every element of S1, so therefore every element of S1 is either nilpotent or unit. Okay, so this is the option C. So option C is again correct. Now let's come to for S2. So B is saying X2 has exactly one maximal ideal, and D, there exists an element in S2 which is neither nilpotent nor unit. So let's come for B. So it is saying that S2 has exactly one maximal ideal, which is Z2X mod x square. S2 has exactly one maximal ideal. Okay, let's do this. Let P be a maximal ideal in S2, means this here Z2X mod x square. Then P corresponds to again a maximal ideal in Z2X containing x square. Let's call it by Q. Then P corresponds to an maximal ideal in Z2X containing x square. Call it, let Q. So x square, this is Q, this is Z2X. So then x square belongs to Q, right? And this is a maximal ideal, means this is a prime ideal, which is again saying that x belongs to Q, right? As Q is prime ideal, because maximal implies prime. So therefore ideal generated by x is contained in Q. Now we'll again show as early that x is a maximal ideal in Z2X. Now again claim. So this is as early x is a maximal ideal in Z2X. Okay, so again we have to, so let P1 as early, we have taken P1 ideal which is strictly contain this x, and we'll take a general element in P1, let P belongs to P1 but not in here. So then you can write Px any general element, then we can write Px as a naught plus x times gx, right? Now a naught, this is in Z2X, so a naught is either 0 or 1, right? Because this is in Z2X. So what will happen? Note that a naught cannot be 0. Note a naught not equals to 0. If a naught equals to 0, then P of x will be x times gx, which implies this belongs to in x, which is not true, right? which is not true. So therefore a naught should be 1. So a naught is 1 means this identity element belongs to in P1, right? Which implies 1 belongs to this here P1. So identity elements belong to this ideal means this is the whole ring, which implies P1 is the Z2X. So which is same as saying that X is a maximal ideal. In Z2X. So therefore X is therefore X equals to this Q, because this is Q is containing X. So therefore X equals to Q, which implies Q is a maximal ideal. In Z2X. So the corresponding ideal, which implies P is a maximal ideal, and which is X, right? So we have started with P is a maximal ideal which contains in S2, right? So P is a maximal ideal in Z2X which contain X square, and we have so Q is a maximal ideal containing X square, and we have shown that Q is ideal generated by X. So means this is the only ideal which contain X square, right? So let me write it here then. So P is a maximal ideal in Z2X mod X square. Q is the only maximal ideal in Z2X. Right, so P will be X mod X square is the only maximal ideal in S2, which is Z2X mod X square, right? Okay, so therefore option number C is again correct. S2 has exactly one maximal ideal. Now option number D. So this is again the option number C, same as. So let's do it. So option number D, saying that S2 has means saying that there exists an element S2 which is neither nilpotent nor unit. So in S2, how the general element will look like? So Px in S2 you can write as A naught plus x gx, this coset, right? This is in S2. What will be the A0? A0 is 0 and 1, right? Because this is in Z2. So if A0 is 0, then Px will be x times gx plus x square, right? So if you take the square, then it will be again 0 element, right? So which implies P of X is nilpotent. Now what happen if A naught is 1? So A naught 1, then P of X will be 1 plus xgx plus the cosec x square. So as xgx is nilpotent, so by the result above, 1 plus xgx plus this x square, so which is P is unit. So therefore, because this is the only choice for A0, 0 and 1, so every element is either nilpotent or unit. So there does not exist any element which is neither nilpotent nor units. So which implies there does not exist any element which is neither nilpotent nor unit. So means there does not exist any element which is neither nilpotent nor unit. So the option number D is false. So here A, B, C are true and D is false. Okay.